So we were discussing about the how an nMOS and Pmos is formed previously. So initially we will be having a wafer. So wafer will be initially pure silicon. If we are using silicon for manufacturing, if we are using germanium, the wafer is purely germanium. Both are group 4 elements. So if we want to create an nMOS, we need to have a P substrate. If we want to generate a Pmos, we need an N substrate. In order to create an N substrate, we have to dope it with group 5 dopants like arsenic, antimony, or bismuth. Here in this diagram, they have doped with arsenic. So you will be getting a free electron here. So it is just a single lattice in a wafer. If you take, you will be having millions of lattices like this. So you will be having millions of free electrons. So if you want to create a P substrate, it has to be doped with group 3 dopants like boron. So you will be having a free hole, positive charge. Actually, hole is not physically a thing. It is a vacancy of electron is mentioned as hole here. So throughout our curriculum, we will be discussing only about nMOS, but I will be discussing PMOS also here. So after discussing ideal IV characteristics also, we will be learning about how we can modify the equations with respect to PMOS. That also we can see. So these are all the symbols of nMOS and PMOS. So these are all the cross-sectional view of nMOS and PMOS. So if you see nMOS, in order to make nMOS, we need a P substrate. So here the silicon lattice is doped with the boron. So in for PMOS, we need N substrate. Here the silicon lattice is doped with the arsenic or antimony. Here this N plus regions for source and drain is formed with respect to uh, group 5 impurities. Here group 4, 3 impurities are used for P plus region and silicon dioxide layer and this is polysilicon gate. Actually, the three regions combined like this bulk, silicon dioxide layer and polysilicon gate, these three things combinedly known as MOS stack, metal oxide semiconductor stacks. Why? Because initially, instead of this polysilicon gate in older technologies, they have used metals as gates instead of polysilicon. That's why the name metal oxide and semiconductor. So, but in actually, this concept is not included in your syllabus. Nowadays, they are not using any uh, semiconductors as these wafers to grow your NMOS or PMOS. Nowadays, they are using insulators. So, the technology named as silicon on insulator (SOI) technology. So recently, all the industries are using only silicon on insulator technology. It is more efficient than what you are studying that MOSFET. So instead of this P or N substrate, they will be using some insulators. Anyway, for any conductivity, we are not uh, actually this P substrate is always grounded with respect to your NMOS, and this N substrate is connected to VDD always. The functionality of this fourth terminal we are not utilizing anywhere, using anyway. So current technology we are not concentrating on semiconductor substrate. We are using only insulators. So we can get into the concept. So initially we need to understand the MOS stack or principle, how a MOS stack has to be activated. Uh, we are going to make use of the regions of operations of the transistor. You might have known that three regions of operations are available for every transistors, irrespective of whether it is an analog or digital transistor. In VLSI, we will be concentrating only on digital transistors. So whether it may be analog or digital, we have three regions of operations. In VLSI concept, we are going to make use of cutoff region as well as saturation region only for explaining all the working of uh, digital, uh, whether a combination or sequential circuits. So if you see the MOS stack, how we are going to use this MOS stack with respect to different voltage conditions. So initially for the gate, we are applying a negative voltage which is less than 0. So the gate is filled with negative charge carriers. So obviously negative charge carriers will attract the positive charge carriers from the uh, substrate. So why it is not crossing or no any electron hole pair recombination, why it is not happening here is in between we have the insulator. So insulator, the silicon dioxide layer won't allow electron or holes to pass through here. So as we are applying a negative charge, this positive charge carriers will accumulate near the silicon dioxide layer. It can't able to pass through. So it will accumulate near the silicon dioxide layer. This region is known as accumulation region. In the second case, we are now increasing the gate voltage above 0, but less than threshold voltage. Here only the concept of threshold voltage is coming. Threshold voltage depends on many parameters. So initially the threshold voltage with respect to the manufacturer. If manufacturer is using silicon, then the threshold voltage ranges between 0.6 to 0.7. If we are using germanium, it ranges between 0.2 to 0.3. And there are a lot of parameters which will affect the threshold voltage that we will be seeing in the non-ideal IV effects. So here what is happening is we are applying a small positive potential to the gate. So now the positive and positive get repel each other, and we will get a region which is neither a positive or nor negative charge carriers accumulated near the silicon dioxide layer. A region which will form which is free of any charge carrier. This is known as depletion region. There won't be any charge. Very vacant positions will be there only. You won't be having any charge carriers there. So the third case, we are again increasing the gate voltage. Now it is greater than the threshold voltage. So it is a more positive potential. What is happening here is your P substrate is having more positive charge carriers, that is your majority charge carriers, and also some minority charge carriers, electrons will be there. So due to this application of high positive potential at the gate, so it will attract the electrons, that is the minority charge carriers beneath the silicon dioxide layer. So initially it was accumulated with positive charge carriers. Now it is negative charge carriers. So inversion is happening here, right? That's why the region is termed as inversion region. So in this inversion region only, channel is going to form between source and drain. So if you want to activate my transistor in linear region or in saturation region, we have to satisfy this condition first. We have to make the gate voltage greater than threshold voltage. Then only the channel will form. After that only, by varying the potential between drain and source, we can able to make the electron to transist from source to drain. So these are all the initial conditions we have to understand. So we have to activate all the uh, um, transistor initially in inversion region by making the gate voltage above the threshold voltage. That was the first thing we have to understand. Then these are now we have to see the conditions for making the transistor to operate in cutoff region, linear region, as well as saturation region. So we have already in IAT one we might have seen some sums. So they will be giving some voltage conditions. We have to specify whether the transistor is working in saturation region or linear region. That we have to specify, right? That is based on these concepts. So if you see here in cutoff region, we are making the transistor or gate voltage, gate to source potential is initially zero. So when we are applying a zero voltage, like what we have specified earlier, there is no positive or negative charge is applied in gate. So nothing is happening here, no channel formation, so no conductivity. So IDS current is zero. Why we are specifying IDS? So the current is flowing from drain to source. That's why IDS is specified, because when we are activating the channel and applying the source and drain potential, the electron will start moving from source to drain. So current will flow in the opposite direction. That's why it is specified as IDS. In cutoff region, we are not applying any proper input voltage. So there is no channel formation. That is, no inversion is happening here. So no output current. So in the second case, B and C image, we are explaining about linear region. The first condition what we have to apply is VGS greater than VT. Now inversion will happen and channel is formed. Now initially, so this voltage condition is very, very important. V that is the potential difference between drain and source. VDS equal to VGS minus VGD. So this is the main equation that relating drain to source potential as well as to drain to gate potential. So initially what we are going to do is we are going to make VGD and VGS equal. So whatever VGS you are applying at the input, same value you are applying between gate and drain. So due to this equation, so VGS and VGD, when it will become zero, so VDS will become zero. That is, there is no potential difference between drain and source. Here, what is the case is channel is formed, electrons are there, but we don't have sufficient potential to or sufficient electric field to make the electrons to move from source to drain. That sufficient pushing force is not there as VDS equal to 0. So in the second case, what we are going to do is we are going to decrease the value of VGD. So initially VGS and VGD was equal. Now we are going to decrease the value of VGD than VGS. So as VGD decreases, we are not going to vary any value of VGS. VGS stands constant here, but we have already in inversion region. VGS stand constant. We are decreasing the VGD value. So automatically VDS will increase. So there will be a positive potential difference between source and drain. So that will generate an electric field. That due to that electric field, your electron will move from source to drain. So consequently, IDS current flow will be opposite direction. So here the condition for another condition is VDS less than VGS minus VT, as we have specified. The third concept is in saturation region. We are again increasing the value of VGS more. And here what we are going to do is we are again decreasing. Here in this case we have seen VGD, even though it is less than VGS, but it is having a value greater than VT. Here what we are going to do, again you are decreasing the value of VGD and you are increasing VGS. You are increasing VGS and again you are decreasing VGD, your VDS will value increase rapidly. So due to this high potential difference, as you may think that as potential difference increases between source and drain, more number of electrons has to be transistor, but it is not happening here. Why? Because even though we have the potential difference high between source and drain, now the VGD, this potential is very less. So due to that, uh, your drain in the region below gate oxide layer near drain, it has no sufficient voltage to attract the electron near silicon dioxide layer. So this region got pinched off due to this low potential difference between gate and drain. But even though current is flowing, why? Because so your drain is in positive potential. Your drain has enough potential to attract this electron from this channel to here. Here this movement is not because of this VGD, sorry, VDS. So it is not happening due to this drain to source potential that we can able to see theoretically by deriving also. As this VGD, drain to gate potential decreases, we don't have enough voltage potential difference, or we don't have enough voltage to attract the electrons from p-type body near the silicon dioxide layer. So a small depletion region formed near drain, so that will reduce the length of the channel. So electron will start flowing from here and only it can reach up to here. We don't have any physical channel. But even though current is flowing, why? Because due to this positive potential in drain. So drain can have enough potential to attract this electron from this channel to drain. So electron is drifting from this channel to drain due to drain potential, not because of VDS. That we can see in detail in that uh, equation. So you have to remember these three voltage conditions initially for cutoff region VGS less than VT, linear region and saturation region. First condition VGS greater than VT. Second condition for linear region VDS less than VGS minus 2 VT, and for saturation region it is greater than VGS minus 2.